Hello there, and welcome everyone to another exciting installment of the Mars Bunker. I'm Ryan MacDonald, and I am delighted to be joined today by Dr. Ali Bramson, a planetary scientist with wide-ranging interests in the geomorphology of other worlds, and who will be shortly starting as an assistant professor at Purdue University. Aha, great. Already see it on the t-shirt. So we're already right there with the theme. So thank you very much for joining us today, Ali. How are you doing today?
Great. Yeah, thanks for having me.
And it's absolutely great to see all the different places that you're all tuning in from today. Hello, I see you from Florida, California, Newcastle on Tyne in the UK. Good choice. And a large Canadian installment we see. Hello there from Ontario. I see we have Copenhagen, Saskatchewan, Stockholm from Sweden. Great to see you all here from all around the world. And we will be taking questions all throughout today's live stream as we meander around all manner of exciting topics surrounding ice on Mars. So I should say that Dr. Bramson has co-authored numerous papers which employ spacecraft remote sensing to study the subsurface ice on the red planet. So last week on the Mars Bunker, we looked at the various ingredients that would be required to survive on Mars and perhaps one day become self-sufficient. Today, we're going to be zooming in on one of perhaps the most important aspects in planning for a sustained human presence on the red planet, namely the location and properties of ice deposits on Mars. So Ali, could you tell us a little bit about what was it that first drew your attention to Mars, and how did you end up researching the red planet?
Yeah, so my research background has sort of spanned like 20 orders of magnitude in size. So I did physics and astrophysics and computer science in undergrad, and I started doing research, and I started in a lab where I was making metal nanoparticles and trying to understand how they break down in different environmental conditions. But that was like sort of too small for me. And I knew I loved space. Since I was like 3 years old, I was going around being like, I'm going to be an astronaut. And I called myself Ali Future Astronaut Bramson. And everyone's like, why is your middle name FA? And I'm like, Future Astronaut. I was a total dork. And so I knew I wanted to do space. And so I wanted to, I started doing research then, more in the astronomy community, doing like galaxy clusters. And then that felt like sort of too big. And then I was really lucky to get into some research programs at Arecibo Observatory down in Puerto Rico, shooting radar beams at asteroids. And then also at the SETI Institute, the Search for Extraterrestrial Intelligence out in California, looking for new lava flows on Io. And that's when I realized that like planets were really my ideal sized body to study. It was so exciting, the idea of being able to like send robots to these other places, these other worlds. And it sort of made me feel like I can be an astronaut from my desk and get to still explore these other planets. And so for me, I've always loved space, but planetary science, I totally fell in love with it once I realized that it was a thing that I could do, and I could use these robots to take pictures. So then I went to grad school for planetary science. And at that point, the main thing that I knew was that I wanted to study sort of surface processes. I love this idea of the tangible aspect of like being able to see a surface and have this observation and want to explain it. And so I chose a PhD program based on where I thought I had the most opportunities to get involved with spacecraft operations and working with spacecraft data. And I have totally had that chance to do that in my career now. And so there's Mars has a lot of active spacecraft missions, and so I've gotten involved in like the Mars Reconnaissance Orbiter, and we had this observation of this weird crater in an area of Mars that we were trying to explain. And then it turned out that it was, we think, due to the presence of this like thick layer of ice in the mid-latitudes. And from there, that's totally set the course for my career.
It's very interesting how these kind of little factors can often lead to divergence in outcomes, because reflecting on it, I had a very similar background. Like, I just studied physics for my undergraduate, and for my master's project, I was essentially manually with a mortar and pestle grinding up surface material to try and make a simulant of Mars or Phobos regolith to look at possible sample return missions to the moons of Mars. And after my little foray into laboratory experiments, I kind of, nope, okay, I'm becoming a theorist now. And then went into exoplanet research. I still hope we can send a spacecraft to those planets one day. But it is very interesting, the huge plethora of opportunities that emerge from just a background in physics, and then planetary science is just a natural way to go into it.
Yeah, and I love how interdisciplinary it is. Like, you can come in from like any background and get involved in the planets. I mean, even like if you're an artist, like NASA needs artists, and all sorts of, there's all sorts of exciting ways to get involved in planetary science. And
because I mean, I know people who've come into exoplanet research from chemistry, biology, from like from geology and geophysics. Yeah, planetary science is just one of the areas where you need to combine so many different disciplines to get a holistic understanding of what planets are actually like, because they're complicated objects.
Yeah. Like, I have an astrophysics background, but now my PhD is in planetary science with like a minor in geosciences. And then I do remote sensing, but now I'm getting back into the lab stuff to study how like ice grains actually like morph and change over time in different planetary conditions. And so sometimes I'm computer programming, and sometimes I'm doing lab stuff, and sometimes I'm, staring at pretty pictures of Mars. And it's such an awesome field.
Yeah, and you mentioned that there was one particular image that you were especially excited by, this crater you mentioned that potentially showed signs of these kind of ice shells. So could you tell us a little bit more about the general background for people who aren't aware about what our current understanding is of how much ice there is on Mars and where on Mars we can find ice?
Yeah, so about like 10 years ago or so, the idea was that most of the water ice that was on Mars was in these polar ice caps, and that the mid-latitudes, these like lower latitude areas, sort of where, the United States is on, those latitudes on Earth, but on Mars, that most of that ice would be sort of, it wouldn't be a ton of ice content. It would be mostly just like the Martian soil or the regolith. And so, so this amazing image is showing the Mars polar ice cap. This is on the north, and that has about as much ice as Greenland, these polar caps. And that any ice at lower latitudes was going to just be water vapor that had settled into the pore space in between all of the little grains of rock. And so you would mostly just have this like dust that's sort of cemented together by ice, and it's still volumetrically mostly rocky material. But in the last
when we look at an image like this, to what extent are we just seeing carbon dioxide ice versus water ice?
Yeah, that's a great question. And that was one thing, a couple decades ago, it was thought that there was a lot of carbon dioxide ice on Mars, and most of the polar caps were made out of it. But actually, it turns out that almost all of the polar caps on Mars are water ice, interestingly enough. And the South Pole, we think there's some sequestered carbon dioxide ice deposits that maybe then got covered in water ice, and that's actually protected those carbon dioxide ice deposits. But so there's enough carbon dioxide ice in the South Pole that if it was released back into the atmosphere, it would double the atmospheric pressure. But actually, when you're looking at images of those polar caps that are kilometers thick, most of that is water ice. But in the last 10 years, we've been finding a lot more evidence that there's actually this like pure ice in the mid latitudes as well. We just, we don't see it because it's not that bright white color, because it's not stable at the surface. But what we're realizing is that there's a bunch in the subsurface, and it's just covered in like a fine layer of dust that's protecting it and thermally insulating it and protecting it from those high temperature swings like in the summer.
So if I'm not mistaken, this image here is showing some evidence of ice in the mid-latitudes on Mars. Yeah. So I presume this has been artificially enhanced in some way when we see these blue streaks here. So can you kind of explain what we're seeing here and how this is, or how we know this is evidence of ice on Mars?
Yeah, so this is a HiRISE image. HiRISE is a camera on the Mars Reconnaissance Orbiter, and it has a 30 centimeter per pixel resolution, which is just mind blowing. Like you can see a table on Mars, you can see the rovers, we can see the rover tracks and follow it around. And so this is a high resolution image, and it's a false color image. So we've got a couple wavelength bands. So it's not like this isn't the exact colors that you would see with your eyes if you were there. And so you can see it wouldn't look that blue, but water ice in the color bands that were picked can show up in bright blue. And those color bands were picked specifically to help us better understand compositions and enhance things in a way that would help us understand what we're looking at. And so in this case, this is a cliff that actually we found that exposes and cuts through some of these thick ice sheets that we think are in the mid-latitudes. And these were just discovered like 2 years ago in these high resolution images. And so that blue section we think is like pretty much almost pure ice to give it that bright blue color. If it was coated in just like a little bit of dust, it would wipe away a lot of that blueness. And we can see that it goes almost all the way up to the surface, and it goes really deep. And so this was an amazing discovery because it connected our ideas that there might be some shallow ice in the upper meter or so with some of the deeper evidence, such as radar, where we thought it was tens of meters deep. Now we think that a lot of this ice is actually in that whole sort of upper tens of meters and connects very shallowly to the surface, just covered in this like fine layer of dust.
So you mentioned about, obviously, a lot of the ice which is being inferred here is subsurface ice. And there's a good reason for this, in fact, illustrated by this question we just got from Bush here about, does the ice go from a solid to a gas or solid to liquid, which is almost like we have prepared, if I can make it work. There we go. So what is it that we're seeing here?
Yeah, so it's a great question. And so with the pressures on Mars, the atmospheric pressure, it's about 1% of the atmosphere of Earth. So because of those reduced pressures, it actually means that the temperatures on Mars, water ice does not go through a liquid phase when it's unstable. It immediately sublimates into water vapor. And so at least in today's climate, we don't really think that there's much in the way of liquid just because of the pressure. And so what happens is ice isn't stable at the surface at these sort of lower latitudes at the non-poles. And so what we have here in this image is that the cameras that we have on Mars, we will image the same part of Mars and like it'll just be a flat surface. And we'll take another image a couple months later, and all of a sudden there's a brand new crater. And so that's a new rock that happened to hit Mars and make a new crater. And at some of these latitudes where we think that there is subsurface ice, actually some of these brand new craters expose and excavate this bright white material that then coats the surface and is in the crater. And that's due to that water ice that's in the subsurface. This is direct evidence that there is ice there. And if you continue imaging that same spot, that same crater, you can see, so this is a time series at the same area. And over the course of like a year, a couple of years, or months, depending on how low of latitude and how warm it is, we actually see all of that bright white material sublimate, and it's going directly into the atmosphere because now it's exposed to the atmosphere. It's too warm and it's not stable, but it's not melting into liquid first. It is just going back and forth between this water vapor and ice form.
And do we know something about the chemical composition of the water here? And what I mean by that is kind of feeding off this question from Peter about whether we have some constraints on whether it's pure water, H2O, or whether it's got some deuterium mixed in there. I know there are measurements of like the D to H ratio, how much deuterium there is relative to hydrogen in Mars's atmosphere. So do we have some way to actually know whether what we're observing has a high fraction of deuterium?
Yeah, that's another really good question. And we don't totally know the answer to that. And that is one of the big outstanding questions that we need to answer before we just go there and plan to use the water ice. And it's also, so I'm really interested in the distribution of water ice on Mars, also from a climate perspective and understanding, okay, the ice isn't stable at these latitudes at the surface today. So this didn't form today. This is a record of a previous climate where it snowed in these areas and then buried it and protected it. And so the exchange from these different ice reservoirs between like the mid-latitudes and the poles. So as that ice exchanges, it can lead to different like D to H ratios, as you mentioned. And so if we can go and directly sample that at some point, that could tell us something about the transport and formation of these different ice deposits and how old they are. And also if they can retain some porosity in them, some airspace or air bubbles. If we go and sample it, there might be a chance that like on Earth with ice cores, we might actually have a sample of what Mars's atmosphere was like in the past when these ice deposits formed at these different sites. And we also don't know like even how much salts are in them. So perchlorates, it turns out, are pretty ubiquitous across Mars, but they would be toxic to life. So we really don't want to go and like drill this ice and just melt it and drink it if there's tons of perchlorates in it. And so even understanding, how much perchlorates could get into the ice, how dirty the ice is in different parts and different deposits. So oftentimes it seems like dust particles and perchlorates even in the atmosphere could act as the nucleating particle for the ice to condense from water vapor in the atmosphere and settle out. So it's very likely that there's these nucleating particles get embedded in the ice when it sort of snows out, either the dust or perchlorates. And so the composition and sort of what's in the ice and these impurities is an outstanding question that is part of where I want to take my research to understand.
And this links in, so we had a question from another space nut about the past atmosphere of Mars. And you mentioned there that if we could get like ice bores or samples by having humans on Mars, we might be able to access those pockets of perhaps the past atmospheric composition. So I was curious, how much do we currently know about the previous climates and atmospheric composition of Mars? And is it a direct inference or kind of indirect from knowing that there once was these water flows on Mars?
Yeah, a lot of it is sort of the indirect evidence and modeling, trying to figure out, using the same physics of how atmospheres work, what would that be like in the past? So the last 3 billion years of Mars's history, we call the Amazonian period. And in this time, most of Mars's climate has been sort of changing just periodically from like obliquity changes. So the tilt of the planet, it wobbles a lot. And Earth
because Mars doesn't have a large moon, of course, and that moon stabilizes it.
Yep. So the Earth, we're sort of stuck at 23.5 degrees tilt, and that gives us our seasons. Even a little bit of wobble there of like a degree can cause that's what we call Milankovitch cycles on Earth, and it can cause like these periodic variations in climate on natural timescales of like, tens of thousands and hundreds of thousands of years.
And meanwhile, Mars is like kind of just flipping about all over the place over geological time.
Yeah, so like without a large stabilizing moon on Mars undergoes really big wobbles, like from 0 degrees down to like, there's basically 100% chance that in Mars's history, it's gone beyond 60 degrees tilt, maybe even 80 degrees or more. And so
it's almost like Uranus then, if it's like getting close to that. That's just crazy.
Uranus is like totally on its side. And so it's really interesting because Mars is sort of a laboratory for sort of natural climate change just due to these periodic variations in the tilt and eccentricity, and without the complicating effects of like an ocean and people and biology. And so, the last 3 billion years, this has been sort of controlling where ice is stable, because when the tilt is low, then your low latitudes and your equator are getting really direct sunlight. And so your low latitudes are really hot. And so ice isn't stable there, but it's really stable at the poles because the poles are really cold. But now when you tilt the planet more, then your poles are getting more direct sunlight. And so now all of a sudden your ice caps at the poles aren't stable anymore. And so that ice will sublimate into the atmosphere and condense out now at your lower latitudes where it's actually colder. And so we think that this sort of back and forth because of the tilt is what's sort of driving the ice moving back and forth between these different latitude bands. And that also determines, so we think that in one of these really low obliquity periods, it was so cold then at the poles, that was actually when a bunch of the carbon dioxide in the atmosphere condensed out into the South Pole and got sequestered in there. And
so could there have been almost a feedback loop there where because of the obliquity taking a certain value, a large amount of the CO2 left the atmosphere, then you have less of a greenhouse effect, and then you can almost kick Mars's climate into a new equilibrium point?
Yeah, and it's a complicated system for sure. And that's where when I mentioned, like, if we could go, so Mars right now, it has about the same obliquity or axial tilt as Earth. And it's been pretty low for the last like 4 million years or so. It shifted down from like 35 degrees to 25 degrees about 4 million years ago. But if Mars were to enter a new sort of obliquity swing where it'd be higher again, now your poles would get a lot of direct sunlight again. And now you could actually sublimate a bunch of that water ice, get back to the carbon dioxide ice that's been sequestered, and release that into the atmosphere. And now you would have an atmosphere that's double the current atmosphere. So we think that Mars is undergoing, even in the last 3 billion years, these periodic variations where you get the whole atmosphere condensing out and you basically have no atmosphere, or today where you have an atmosphere that's about 1% of Earth's atmosphere, or in times of high obliquity, then you have an atmosphere that's twice as thick. And so yeah, Mars has a very active atmosphere, and we actually think something similar is happening on Pluto, interestingly enough, with like nitrogen ice, which is really cool.
That gives me an idea of almost a very supervillain way to terraform Mars. If we can just, tilt the obliquity of the planet for a little bit, wait for the polar ice cap to sublime, then tilt it back.
Yeah. Yeah, I mean, even if we double the atmospheric pressure on Mars by releasing the sequestered carbon dioxide, it's still going to be only about 2% of Earth's atmosphere. But that's enough.
You've got a long way to go.
Yeah, but Mars definitely has an atmosphere. Like that is enough to have dust devils that are taller than Mount Everest, and ice and frost and clouds and all sorts of amazing global dust storms, which unfortunately then block out the sunlight and kill our rovers, RIP. And so yeah, the atmosphere today is still enough that it's causing Mars to be a very dynamic process, but a very dynamic place. I mean, but we think, yeah, beyond the Amazonian, like sort of 4.5 billion years ago to 3 billion years ago, that it had an even thicker atmosphere. And because Mars is so small, it doesn't have as much gravity. And so over time, it's been losing its atmosphere. That's why we're at only about 1% today compared to what we think was a thick atmosphere that could have made Mars a lot warmer and wetter place about like 4 billion years ago. And so the MAVEN mission, it's a NASA mission that's orbiting Mars. And that's actually its main science goals, is to understand the atmospheric loss processes.
And I think I remember hearing some of the estimated figures from MAVEN that it's not just about Mars's atmosphere escaping. A lot of the water content from ancient Mars would have been lost to space as well. Correct me if I'm wrong, but I think the figure I was remembering off the top of my head was about 70% water loss. So do we know how much water there is still on Mars today locked in the form of ice, whether that be at the ice caps or subsurface ice sheets?
Yeah, so that's an active area of my research. So thanks for that question. So like I mentioned, the ice caps on Mars have they have enough ice that it's about the size of Greenland on Earth. And so in my research, I've been trying to understand how much ice is there in the mid-latitudes and these non-polar areas of Mars buried in the subsurface. And so I use radar and images of like funky craters, because craters are sort of a probe into the subsurface. And yeah, trying to piece together all the different data sets of what we can learn about the subsurface. And so I'm involved in a project called the SWIM project, and that's what's being shown here on the screen. And SWIM stands for Subsurface Water Ice Mapping. And so this is showing our initial results for the Northern Hemisphere. And what we're doing in the SWIM project is we're trying to combine all the different data sets that we currently have of Mars, from like thermal data, like what are the temperature swings of the surface and what does that mean? So different materials have different properties that exhibit different signatures sort of in the thermal data, and also even like neutron spectroscopy can detect hydrogen in the subsurface in the upper meter. I use radar a lot to try to look into the subsurface and find layers, and not to mention those images of new impact craters and those icy scarps that are providing the direct evidence. And so the SWIM project, the goal is really to combine all the data sets. For so long we've been using several different geophysical methods, addressing Camille's question. And so I think we're at the stage now that we're sort of on the cusp of unlocking what the mid-latitudes are telling us, but we need to combine all these different data sets. And so what this plot is showing us, we've developed what we're calling the SWIM equation, which is sort of in lieu of like the Drake equation, where each of these different data sets, we're saying, okay, how consistent for a given area, how consistent is this data with the absence or presence of water ice? And so we're assigning values. So 1 would mean this type of data set is like wholly consistent with the presence of water ice here. And a -1, we're saying, okay, totally not consistent with ice. This is like a lava flow or something. And we're adding up all of these different data sets together and trying to find what areas of Mars do the most data sets tell us have water ice. And it's tricky because all these different data sets sense different sort of depths and different things. So like the thermal data senses like the upper meter or so, as well as neutron spectroscopy, whereas the radar is looking tens of meters deep. So it's tricky. It's not, it's not easy. And ultimately, if we want to confirm a lot of this, we're going to need a new mission to Mars. But you can see in this map, so the blue is what we're saying is a high consistency, and red is low consistency. And you can see that across much of the mid-latitudes, we are finding there are blue areas. There are multiple data sets that are consistent with the presence of ice. And Arcadia Planitia is probably one of, if not the best, area because there's the most data sets suggesting that there is ice there, and it goes to the lowest latitudes. And there's also Onylus. There's a bunch of like old glaciers in that area too, but it's going to be, sort of to the left. But you can see it's located in very like discrete inside valleys and stuff, whereas Arcadia is this like wide plains area, and we are finding a lot of evidence that there's ice across the whole area. So it might be this like big resource that's easy to access, easy being, I throw around that term extremely loosely.
And so this is just for the Northern Hemisphere. So here's the equator, everyone, and then north of that. Are you planning to extend the SWIM survey to the Southern Hemisphere and see if, I don't know if there's any ice in, let's say like the Hellas Basin or some of the other impact basins down there?
Yeah, so that's what we're working on right now, actually. And we're hoping to finish up the Southern Hemisphere, at least for any elevations that are below 1 kilometer is what we're funded to work on. So that elevation constraint is because you need to safely land on Mars, you oftentimes need to go through more atmosphere to use your parachute to slow down. So we actually, basically, if we're going to send missions and humans one day, we will probably want to land at an elevation that's below 1 kilometer. So most of the Northern Hemisphere meets that criteria, but the Southern Hemisphere is higher elevation, and it's also a lot more rugged and a lot rougher. And so we are working on the Southern Hemisphere, but it is trickier because there's not these like big flat plains areas. And so we're looking, and we're hoping to have the Southern Hemisphere products available sometime this summer, but we're not finding quite as extensive of evidence as the Northern Hemisphere. There's certainly like some of the similar geomorphologies that we see that we think are due to icy surfaces, like where we think there's like collapse features that we think are from the ice sublimating out of the subsurface, and then the surface collapses because that ice isn't there anymore. But the Southern Hemisphere would be a lot trickier. And so the Northern Hemisphere is probably where it's at if you want to go to find ice resources.
So I think we're going to take about 10 minutes now to look at some of the questions that you've all been sending in. And please do keep sending them in, and everyone, because they're absolutely fantastic. So, for example, this is a question from David Johnson, similar, effectively asking about the properties or the toxicity of ice on Mars. And asking, so you already mentioned, Ali, about these perchlorates, for example. Is there anything we can do with remote sensing, perhaps? I don't know whether we'd need a new mission, like David is suggesting there, to assess this, or do we actually have to go to the ground to really understand what this ice is like?
Yeah, I think we definitely are going to need a new mission to confirm a lot of these things, especially, I think, to get at, so some of the geophysical sensing techniques can get at some aspects of like the composition. Some things can help us infer how dusty or icy, sort of what that ratio is. But I think to be able to figure out how much perchlorates are mixed in, or like, you know, if we want to get at like D to H ratios, like we're going to need to sample it. And right now, like our best way of sampling this ice is from those, just having these images of the new impacts and these icy scarps. But honestly, I feel like we're sort of reaching the limit of how much we can learn with the current data sets. Like I said, the SWIM project is like trying to integrate all these data sets, and we're doing the best we can. But if we really want to know the properties well enough to be able to use it as a resource for human exploration, and even to sample it for understanding like if there's little like old atmospheric air bubbles in it, we're going to need a new mission. We'll probably need to sample the ice on Mars at some point, which would be really tricky. And for now, in terms of like just even understanding where the ice is, how much is there, and how shallowly it's buried. So if it's only like 10 centimeters under the surface, or if it's like 3 meters under the surface, that's going to have a huge implication for what sort of drilling technology you need. Like, can you send somebody with just like a shovel to get at it, or are you going to need like a drill? And that's where there's this gap in our knowledge right now, where we've got sensing techniques that can see sort of in the upper meter, and then we've got radar that can look at like sort of tens of meters. So we really have this gap in sensing with our current observations and the current sort of fleet of instruments on Mars right now. We're sort of lacking what is going on in like sort of from about a meter to 20 meters. And that's going to be the most exciting area for where the Mars is, where the ice is, and what's going on with it. And so one thing that we've been sort of proposing is possibly like a higher frequency radar. So it would have a smaller wavelength. And so we could hopefully see sort of in that
like finer spatial resolution. That would be the idea.
Yeah. So right now, SHARAD, the shallow radar, it's on board the Mars Reconnaissance Orbiter. It was built and provided by the Italian Space Agency. It has a resolution of about 10 meters, but that surface, that interface between the atmosphere and the surface sort of shows up so brightly in the radar data that we can't really see anything within like 25 meters of the surface. And so,
and also, if you wanted to extract something, if you were actually there, the first 25 meters is critical, because it's a lot harder in the early stages to get to the deeper depths.
Yeah. So we're really advocating for a higher frequency radar at Mars. And again, I think one thing that would need to be done if we're going to go there for human exploration is we would want to send a robotic mission first that would hopefully sample the ice and test some of these like drilling and extraction technologies, because we do have a lot of outstanding questions still about the ice, and we're sort of reaching the limit of what we can do with the current assets.
So here's a question from Usenerd. So I think you have you done some field research, at least on Earth yourself?
Yeah.
Would you sign up to do field research on Mars given the chance?
I think so. I would love to go to space. I would go to the moon in a heartbeat. I think we're still pretty far from going to Mars, honestly. I mean, it's a big difference going somewhere that's a 9-month journey on a rocket than somewhere that's a 3-day journey, especially when we still have so many technologies to develop. So I would love to go there, and but yeah, we need to figure out like the radiation shielding for protecting our humans in the rocket on the way there, and hopefully being able to access some of these water resources to convert it into fuel to enable a journey back, so it's not a one-way journey, or if something goes wrong, we can get people back. But I mean, yeah, the idea of like going and sampling the ice that I study and like seeing it with my own eyes would be, you know, a dream. It would be amazing. I actually do dream about it. And yeah, I have done field research on Earth at like analog sites to try to understand like how do you get layering in ice, and how detectable is it with radar here on Earth, and what can that tell us about developing technologies for detecting it on Mars. So field research, again, that like shows how interdisciplinary this field really is, that, you know, you can be hanging out in a glacier in Iceland, or you can be in the lab, or you can be doing like coding of computer models, or staring at pretty pictures of new craters. And there's so many different ways to try to approach these problems and understand the ice. And the further I get in this field, the more I'm just like opening myself up to doing any type of research it takes to understanding the ice. And so I'm really trying to combine lots of different types of studies to figure out what is going on Mars and how much ice is there. And especially now that, you know, we think if you add up all of these different things, we think that like there, of all of the Mars ice, like 25% of it could actually be in the mid latitudes. It's not all at the poles. And so, yeah, how do we understand it? There's lots of different ways to explore it. But ultimately, I think before we send humans, we will want another robotic mission to confirm a lot of these things before we, you know, bank human lives on on the ice.
Yeah. So we're also getting a lot of questions about perhaps something that could be on such a robotic precursor mission, about extracting Martian ice. So I'll just highlight kind of 3 of them here. So Starman asks, do we know what the most effective way to extract it would be? And lots of people are pointing out this thing. As we mentioned already, ice on Mars sublimates reasonably rapidly. How do we extract it if that's an issue? So that's one part. How do we extract it? And also questions from Dale about, once we've extracted it, can we remove perchlorates and other possible toxic compounds by distilling it? And Miko was also kind of chipping in on that topic. So extracting ice and perhaps turning it into water, how much still needs to be done on that front? Like, essentially, what still needs to be understood about extracting and purifying Martian ice?
Yeah, I mean, that's still a big area that would need to be developed as well. So there's some people are looking into like Rodriguez wells, which is a drilling technology for drilling into ice. But, you know, a lot of this depends on these things that we're still trying to understand, like how deep the ice is, even like how dusty it is or how much porosity is in it is going to determine how hard it is to drill into it. As people mentioned, you could probably distill it to get impurities out. So a lot of it is like, how do you access it, or and keep it contained so it doesn't sublimate. I mean, the craters we looked at earlier, that was over the course of like several months or even sometimes years. So it's not like if you expose it,
you don't just dig a hole and it's gone.
Yeah, so you'll have a little bit of time to deal with it, but I mean, you would want to keep it sort of contained in some container so you can use it as you need it. And I think so NASA has been starting to organize like these Mars human exploration workshops. There was one, I think, in 2015. And there's one, I think it was supposed to be this fall that we were supposed to present the SWIM project results at, but at this point, it might get pushed to later, obviously, with the global pandemic. But yeah, so the next workshop, it'll be great because it'll bring together the science community with the engineers who are working on some of these technologies. And I think at the last workshop, it was thrown about that like for each human crew that you would send, you would probably need like 20 metric tons of water ice resources. And so, yeah, the drilling technology is not there. I mean, so I've done field work at the Langjökull Glacier in Iceland, where we were trying to relate the layers we saw in radar that we took from the surface with then taking ice cores through the glacier. And, you know, even on Earth, it can be hard to drill. Sometimes your drill gets stuck. What do you do if you send a robotic drill to Mars and it gets stuck? And that's what we're trying to even deal with right now with the InSight lander. The InSight has a probe that it's been trying to drill to take essentially the temperature of Mars, and that drill just keeps getting stuck. And that's not at an icy location, but you know, drilling technology it's hard. And so there's a lot of technology development that needs to happen. But the exciting thing is that, you know, all of this stuff that's happening for space exploration, this gives us new technologies and really exciting things that we can then, you know, apply to our own planet. And so, you know, one thing that I think is really exciting is that in space exploration, we never know what things that we're discovering or what applications are going to end up, you know, becoming the internet or cell phones. And so, you know, anything that we're working on for this problem is surely going to yield technologies that are really useful on Earth too.
And I thought it'd be nice to kind of illustrate it here with these two images that you kindly sent, showing the similarities between some of the systems we find on Mars versus on Earth, and how often Earth can provide good analogs in preparing for Mars, but equally what we learn on Mars can tell us much more about the general processes that are going on and get a better understanding of how they influence not just one planet, but planets in general.
Yeah, I love this set of images. So my office mate, Eric Peterson, and Jack Holt provided this image on the right is of Sourdough Glacier in Alaska. And the image on the left is actually a remnant glacier on Mars. And it's like so cool to see the similarities, and just you get this like lobate flow front and all these like, yeah, flow features, and comparing and contrasting features on the different planets can tell us how these processes work. I mean, ultimately, it's the same underlying physics, you know, just some different parameters, different gravity or different atmospheric compositions. And so it can tell us about how the process even works here on Earth. And so, yeah, studying some of these features and how we would be able to, you know, uncover all of like that rocky material that's on top of this glacier on Earth could then be applied to, you know, if we wanted to drill at this glacier on Mars, how do we do that and get rid of all the boulders and stuff that are on top that have fallen off of sort of that cliff that the glacier has carved through.
So we also had a question. So we've talked about these ice glaciers that you can find on Mars, and we had a specific question from Dana here about the thickness of some of these ice systems, specifically the thickness of the ice close to Erebus Mons.
Mm-hmm.
So yeah, how thick are these things? Are they like a meter, or are they like these thick, I don't know, multi-kilometer things? So try and ground us. Yeah,
that's a great question. So, and yeah, I've been sort of talking about like different forms of where we think there's ice. We think there's some probably widespread ice across the plains, and that is probably on the order of tens of meters thick, or up to like 100. Those icy cliff sites show about that cliff. There wasn't really a scale bar to get a sense of like vertical scale, but that was about 100 meters. And and that doesn't even expose all the way to the bottom. That's not necessarily, there's a layer of debris that is sort of covering the bottom. So we don't know that that's actually, the ice could continue even deeper into the subsurface. It just hasn't been exposed yet. Meanwhile, those glacial features can be like a kilometer thick. So we do likely have thick deposits that could be accessed. And I think one of the big questions is, how much do you need to drill at the top surface level to get into them? And the glacier features are more likely to have a really rugged terrain on top with lots of big boulders that have fallen off of like the head walls on those mountains, whereas the flat plains area is probably more likely to be like consolidated dust. But it also can still have like blocky boulders and stuff too. So that's one of the things that oftentimes sets what is like a safe landing site, is how rugged and blocky and bouldery the terrain is. And it's a lot more likely that those glaciers are going to be really rough and bouldery compared to the flat plains areas. But as they mentioned with like Erebus Montes, so actually in southern Arcadia Planitia, there's Phlegromontes and Erebus Montes. Those are two areas with sort of some mountains. That's what Montes means, is mountains. And so southern Arcadia might actually be an ideal site because there's, and this is showing the results from the swim equation, our initial results. So in southern Arcadia, there's actually some of this plains, the flat plains areas, but there's also some of these mountains which look to have some of these glacial landforms emerging off of them. So it might be the best of both worlds, where we can access some of the glacial ice and some of sort of the flat plains ice. And so, I think this is showing some of like the sort of proposed sites possibly.
Yeah, so these 8 points are showing some of the places that SpaceX are considering for potential landing sites in Arcadia Planitia. They're not fixed yet. These are just areas where high-resolution photographs have been requested. But I think it's a really nice illustration when plotted on top of the swim results that these tend to be areas with very high water ice consistency. So it just shows how crucial the ice will be for perhaps even, maybe even one day, the site of the first landing of people on Mars will be determined crucially by your equation. Wouldn't that be incredible?
I know. It's like, it's sort of, like some days when I'm working on like the swim stuff, or a couple years ago when I was working on my PhD at the time, and meeting with some people at SpaceX and talking about Arcadia Planitia, I was like, oh my gosh, what if my work like sets where humans go one day? It's so mind blowing to think that like, that I maybe could help influence this. But it's been really exciting to see the results of the swim equation and our mapping come out, because the graph that not the graph, but the figure that we had shown before, all of the white dots that were on there were where, this one, the white dots are where there are new impacts that happen to expose that water ice. And so, there's nothing in what we're doing inherently that would cause that to match up that nicely. Like, we're not actually using the ice exposing impacts in the swim equation. We're using them actually to validate it independently. And you can see that all of these ice exposing impacts are very nicely in the regions that are coming out blue in our work. And so that's really reassuring that we're on the right track.
By the way, is there a reason why there isn't coverage in the initial results of the Tharsis region over here?
Yeah, so initially the project, we were only funded to do, it's been sort of growing actually. Initially the project was just for like a pilot study in Arcadia Planitia. And then it's been, then we got funding from NASA to expand to most of the Northern Hemisphere. But most of that area that's sort of grayed out is where there's a bunch of volcanoes. So you can sort of see right on the left edge of that, that's Olympus Mons. That's the largest volcano in the solar system. And so most of that area is higher elevation than 1 kilometer. And so a lot of it is like we sort of know as lava flows around there, and at high elevation, which would be really hard to land because you just don't have enough atmosphere to slow your lander down. And so initially, yeah, it was like, we're trying to crank out these products quickly because it's such a topical thing right now. And so we got funding to do, sort of Onylus, Utopia, Arcadia, and Acidalia. But now with expanding it to be more global, we are looking in that area, at least at the areas that are below this like 1 kilometer elevation cutoff.
So I would also just like to say thank you very much, Warhawk, for the super chat there. And thank you as well, Ali, for obviously being such a wonderful guest. We're certainly learning a lot, and we will try and in our remaining time take many more of your questions. I'm just seeing... there was one thing that I really wanted to touch upon, which was another aspect of your research. We've talked a lot about the ice on Mars, but I recall, I think, was it in the last year or 2 years, you co-authored a paper looking at the possibility of subsurface water underneath the southern polar ice cap. I think it was you were doing some modeling to try and interpret some Mars Express observations.
Yeah.
So could you tell us a little bit more about that?
Yeah. So one thing that I'm really interested in is, could these ice deposits interact with higher heat flow from the inside of Mars? So we know that Mars has had volcanism in the past. We have, all these old volcanoes dotting the surface. So if there was a magma chamber under the surface of Mars recently, could the heat from that, even if it doesn't come up to the surface and erupt, just by being in the subsurface, that heat flow can make it up to the surface? Could that interact with these ice sheets and actually help create conditions for liquid water and melting? And so
almost like there are questions just anticipating this.
Yeah. So in 2018, there's a Italian radar group that published a paper where they were looking at the south pole of Mars in the radar data, and they found some really bright reflectors, is what we call it. That's where the radar bounces off of some interface in the subsurface. And they found a really bright reflector at the base of the South Pole. And they argued that that is due to the presence of liquid water, because liquid water has a really big contrast in properties to solid materials like ice and rock. And so they argued that it was so bright that you would need some liquid water there. And so we're trying to follow up on that study and see what is the likelihood, or what conditions do you need to actually get liquid water there. My co-author and I, we modeled what sort of salt contents and heat fluxes would you need to actually melt the ice? Because in that Italian paper, they said, like, oh, well, we know there's salts on Mars, and salts lower the freezing point and make it easier to melt. So, maybe it's just salty there, and that leads to liquid water. And so we wanted to test that hypothesis. And what we found is that under today's expected heat flow, that's just sort of remnant in the inside of Mars, you can't get liquid water to melt, even with like ideal salt content. We looked at like sodium perchlorates, calcium perchlorates. We looked at a couple different salt contents. Even if you have like the maximum best perchlorate down there, you can't get melting. And what we found is that you need an increased heat flow from below. So it's sort of like how if you throw a turkey in the oven, it takes a while to get that heat into the middle of the turkey. So similarly, it takes time for heat to diffuse outward. So that magma chamber, you need to have a magma chamber with increased heat right below the South Pole recently to be able to melt the ice, even under ideal sort of salty conditions. And so that means that we sort of raise the possibility that has Mars been volcanically or magmatically active recently?
I was going to ask whether InSight could potentially corroborate some of those findings. I don't know if you would expect there to be some kind of seismic evidence for a recent magma chamber under the South Pole. So I'm curious about ways to test that hypothesis.
Yeah, and we were really excited to get InSight's geothermal heat probe results, but unfortunately that's the probe that has gotten stuck, and it is having a really hard time and is a bit on the struggle bus because apparently Mars is not wanting to be drilled at. And so, yeah, we were really looking forward to using the InSight results. And I mean, ultimately, that would only be at one place that's really far away from the poles. But InSight is telling us that Mars is still pretty active today. They're finding results of seismic activity, and so it's likely that, yeah, I go sort of back and forth of like how plausible I think it is. Like, oh, could we have a magma chamber there today? Could we not? And so it sort of opens up the debate about if there's liquid water on Mars and takes it in another direction of like, okay, well, let's now consider how likely it is to have an active magma chamber on Earth. And we think that there's some lava flows on the surface of Mars that like crater counting has suggested are on the order of like maybe even millions of years, which on geologic time is recent. And so, so yeah, maybe, yeah, one direction that I'm exploring now in my own research is how often has magma chambers and Mars volcanism and interior processes actually contributed to melting these sort of surface ice deposits in the past, and how likely could we have actually had liquid water melting, even if the atmospheric conditions don't allow it? Maybe the interior conditions do allow it.
So, and thank you, David, for a super chat about almost, I imagine this is more, when would be the next opportunity for you to send an experiment to Mars? And perhaps even what would be your dream experiment if you could send one thing to learn about ice on Mars?
Yeah. So I was involved in a mission proposal that went into NASA, but unfortunately was not selected. That would have been to send a new orbiter to Mars that would have this higher frequency radar on board, as well as some other instruments to try to understand like the water vapor content in the atmosphere, how concentrated is it near the surface, because that can tell you how stable the ice is. But really, yeah, that higher frequency radar would have been awesome for trying to understand what is going on in the upper 10 meters or so. But the president's budget request that came out, I guess like a month and a half ago or so, sort of as a surprise to the community, had a Mars IceMapper line item in there that we are all now very eagerly dissecting and trying to...
Did this come completely out of the blue? Hey everyone, here's money to map ice on Mars. Wait, what? Did we ask for this?
Yeah, I mean, someone had to have asked for it somewhere along the way, and certainly the Mars ice and polar community has been building up to something like that. So it's sort of nice to feel like we're getting heard, that this is something that, you know, the high ups are thinking is important for human exploration. It would be, from what we can tell, it would be part of, yeah, the human exploration side of things, and this whole Moon to Mars new program where we're going to try to go to the moon first and sort of perfect technologies for human exploration, and then that's going to be a stepping stone for Mars. But, you know, there's so many things that show up in presidential and congressional line item budget drafts that, you know, never see the light of actual day. So it's hard to know what's going to happen, but it is encouraging to those of us that study Mars ice that, you know, the community is really advocating for something like this. And we hope that something could happen, you know, in the next decade. Right now, the planetary science community, we're gearing up for what we call the decadal survey, where it's just where the community comes together.
Yeah, we've got a similar one in astrophysics coming up as well.
Yeah, and earth science and heliophysics also. They each have their own decadal survey, and the community comes together and puts together, this is our priorities for the next 10 years. And so, you know, I'm going to be a strong advocate for Mars mid-latitude ice, and hoping to get it on the priority list so that we can send that to NASA and be like, this, you know, we need this to happen in the next 10 years. So ideally, to sort of go back to the question that was asked, ideally we would try to get this on the docket for a new mission within the next 10 years. And honestly, we really need a new Mars orbiter. The Mars Reconnaissance Orbiter, it launched in 2005. It's aging, its gyro wheels are struggling to maintain its pointing. It's aging. And the thing is, these
And of course,
orbiters,
these orbiters are all use the relays for the missions on the surface, like InSight, and so you can't get the data back without them.
yeah, and so that's the important thing is like even besides the science and the resource aspect of mapping the ice, we really need another orbiter that can help relay. Especially, we're sending in July, the Mars 2020 Perseverance rover is launching, and these surface assets, these surface rovers, they use the orbiters, they send their signals to the orbiters, and the orbiters send those back to Earth. And so with an aging orbital fleet, it's gonna suck to send a brand new shiny rover there if
you can't get the data back.
Yeah, and so, I think sometimes in the right configuration, it might be able to send like a small direct signal to Earth, but not nearly what you need to send all the data back and to have like these very regular communications. And so we need a new Mars orbiter. We need it soon. It's also interesting being in this field because things don't happen quickly. Like missions take a long time to develop and build. Like, it's so weird being like when I was on putting together this mission concept for this last, what we call the discovery round. It's sort of a small, medium class of mission. I was having to put together a budget for like the year 2041 for myself for the science I would do if this thing was selected. And so it's a really long game that we're playing, and so it's interesting because we can't just like go down the lab and get all of our data. We need to plan 10 years ahead of time for these new missions to make them happen, not to mention the time that it takes, just the travel time. The outer solar system is even, more, is even harder and longer to get to. So being in this field, it's exciting being, a relatively young person in the field because there's just a lot to look forward to for the rest of my career. But it also means we want to advocate for this stuff now because it might not happen for 10 years.
Yeah, we have a very similar thing in astrophysics. Like the early plans for James Webb were being written in like the late 80s, and we're still waiting for the thing to launch. And
Right.
I know we're past the 1 hour mark, everyone, but I think we could cover one final question since loads of you have raised this question. And since you mentioned the decadal survey, it was also the priority of the 2010 survey. Namely, so many people are asking about sample return and especially about ice sample return. I'll try and highlight some of them. And thanks for your patience, everyone, while we've been looking at all the other topics. So, Raj was asking about sample return. I also saw so many questions. Peter saying sample return, sample return, sample return. It's a very, very popular topic. So, and Adam Synergy was wondering about could ice even survive sample return? So yeah, is anything potentially on the radar, pardon the pun, for returning Martian ice to Earth?
Yeah, unfortunately, there are no plans to return Martian ice. All the plans are for the Mars 2020 Perseverance rover to collect samples at Jezero crater. And then right now the infrastructure is being developed in collaboration with the European Space Agency to then develop another mission that would go and pick up the samples and send them back to Earth. So right now the plan is all the samples would be from Jezero crater, which is thought to be an ancient lake bed. And so the idea is to go to a crater that's big and is excavated deep into the subsurface where you're exposing rocks from back in that time when Mars was warmer and wetter to try to understand the habitability of Mars early in its history. So the focus isn't necessarily on like this Amazonian aged processes that I mentioned, like where we've got a lot of this like ice moving about. Also, there's a problem with there's a thing called planetary protection. And so this is the idea of, first of all, we don't want to send our microbes and bugs to Mars and potentially contaminate it. And also, if another place in space has microbes, we don't want to necessarily send them back to Earth either. Like if we don't decontaminate our spacecraft properly and it goes to the surface of Mars, and then 20 years down the line we have another mission trying to detect life on Mars, we want to make sure we can unambiguously figure out if there's life elsewhere and it's not just stuff that we brought accidentally. And so right now with the way planetary protection is written, it makes it really hard to actually go directly to the ice on Mars because there is a concern. What if you have a nuclear power source on a rover and that would accidentally melt the ice and be liquid water, and then we would like introduce microbes into the system. And so right now we have mostly orbiter technologies that are looking at the ice instead of going there directly. But the Phoenix lander back in the 2000s, it went to the high mid-latitudes or the low polar areas at like 68 degrees north. And it actually went to an icy site, and it had a little digger, and it scooped away some of the dust. And within a couple centimeters, it was finding water ice. So it's been done before, but yeah, right now there's really nothing on NASA's plans for sampling the ice, and definitely there's nothing for bringing it back. Bringing it back would be really tricky. It's already hard figuring out how to bring some rocks back, let alone keeping ice in ice form.
All the more reasons to send human explorers one day to explore the Martian ice in situ and see what we can learn about the secrets that Mars. Yep, with a shovel or whether we're drilling, the ice holds the secrets to the past and to our future.
Yeah,
this is one thing that I really like about this. So I think we'll pretty much just wrap up there. But one note that I did want to leave this on, and another space nut says, thank you, Ali, on behalf of all the community for enlightening us on all of this. So Dan just pointed out that he's just finished his master's thesis on Martian brines and that your research is really interesting. So you'll be starting as an assistant professor shortly, and you're looking for graduate students. So can you tell us a little bit more about that, and perhaps if there's anyone watching today who could be interested in working with you, how they could get in touch with you?
Yeah. So as Ryan mentioned, I'm about to start a professor position at Purdue University, and I'm really excited because it means I'm going to be building up my own research group. So actually, I have 2 PhD students starting with me this fall who are going to study Mars ice, and certainly over the next several years, I'm going to be, and hopefully like decades and my whole career, I'm going to be looking to, grow a research group and take undergrad students, masters, hopefully, and especially PhD students to do research with me on these topics. And so yeah, anybody that is interested in doing research and potentially coming to Purdue University, we have an amazing, growing, really vibrant planetary science group there in the Department of Earth, Atmospheric and Planetary Sciences. And so, feel free to reach out. You can look up at the department website. You can find our email addresses. You can find my Purdue email address, and feel free to reach out if this is a topic that you're interested in pursuing in grad school. Or I'm also looking to have undergrads at Purdue help me in building up my research group as well. So I would love to, have a fun research group. And I'm excited to be starting in the fall and have my own research group to work on these exciting things. So shout out to Riley and Chris who are joining me starting right away in August. We're gonna have an awesome time.
And as Alan says, go to glaciers.
Yeah.
So that's all the avenues that you have potentially if you're interested in researching this field to potentially work with Ali. And if you're also interested in helping out, I am pleased to say that within the last week, we launched the beta test of my own Martian Colonist Discord channel. And we're starting to do early research for the next Mars mission update. So if you would potentially be interested in joining our research team in preparing for future live streams and also for future videos in this channel, if you go on my YouTube channel page and go to About, you can find my email address there. Just write an email to me saying you'd like to join the Discord server, and we'd be happy to have you on there. Keep an eye out next week as well. There'll be an announcement on Twitter for the next guest in the Mars bunker. But for now, everyone, please, everyone, extend your thanks to Ali, our guest today. That was absolutely fascinating. And we'll see you all next week in the Mars bunker. Bye there, everyone.
Hi, thanks, everyone.